the morning. So the first talk is going to be Nicholas Beiser from ETA. He's going to tell us about smooth Wilson loops.
Okay, thanks for the introduction. I'll talk about smooth Wilson loops and also about Young symmetry in exposed nuclear mills. This is joint work with Jan's student Dennis and Christian, and also some, which is partly appeared, and hopefully the rest will soon appear. And the second part will be about work with my student Alexander. This is very much work in progress, so things there can actually change. So let me start by really thanking the organizers for being so excessively kind to me by displaying my name so prominently in the poster and putting all the places I've been at some point. Here, I don't know that this is kind. Thanks for the honor. So let me start with the motivation for my talk. So we all know that NH is supposed to be non-disintegrable, and there really cannot be any reasonable doubt. But every now and then someone asks me and asks, is it actually integrable? And then that's a difficult question because actually there are many answers. Or first of all, there are actually many definitions of integrability. So the question would be, what does it mean for this theory to be integrable? But then again, maybe I'm a pragmatic guy, and I usually give an answer of the kind, well, you know, if there has been 10 years of IGST conferences, it surely is integrable. And then there are so many interesting applications. So, but the question would be, can we actually show it beyond, testing it further and further with different means? So one definition of integrability is Youngian symmetry, and you can look at various types of observables. Maybe the first and most prominent one is the spectrum of local operators. Unfortunately, there, you do have Youngian symmetry, but the symmetry is actually broken by the boundaries because the thing you're looking at, the Hamiltonian or the dilatation operator, has a large n topology of an annulus, and that the Youngian doesn't really like, or you cannot easily make statements. And furthermore, the Hamiltonian is not exactly known, so we don't actually know how to act on things. Now the other type of observable that gave me good hope that I want to make progress is scattering amplitude with null polygonal Wilson loops. And that's nice because for this observable you do have a large n-disk topology, and the Youngian likes to, or is able to in principle annihilate these things. But on the other hand, it turned out, at NH3 level you did see a lot of Youngian symmetry, but then if you go to loop level, then the symmetry is broken by infrared or ultraviolet divergences, and it's not really clear how to deal with this situation. So I'm afraid I have to say that amplitudes are not terribly useful. And this week I can say this, but this is very much a personal statement. So I'm not sure how to actually make use of Youngian symmetry for this type of observable, but this might not be the final word. The people have indeed made good use of that. But in terms of, say, proofs or mathematical statements, it's not so. Okay. Now, there is indeed one object which deserves, and those are smooth Wilson loops, which sort of combines the nice features of these two. On the one hand, this is indeed a finite observable, and furthermore, you can look at this topology in the large n limit, and so this would be an object where you can really properly see Youngian invariants. So let me start with right into the subject with these Maldassena Wilson loops. So we can define finite Wilson loops in n equals close to bare mills, and this was more or less one of the applications of the IGST correspondence, where you, in addition to the usual coupling to the gauge field, you add a coupling to the scalars, make sure the coupling is of same strength between the scalars and the gauge field. And then one of the problems of the null polygonal Wilson loops was that they are null, but here here, this path that you choose is actually non-null in 4 dimensions, but in this extended 10-dimensional space where you take the scalar couplings into account, and since somehow the length of this path counts and the length is 0, so the usual perimeter divergence of the Wilson loop goes away because the perimeter is null. And furthermore, it's a locally supersymmetric object, and therefore you would also expect things to be finite. Now, for the Youngian, that's very useful because you have a finite observable, and you could, in principle, make meaningful statements without discussing regularization issues, renormalization issues. But one slight problem is that you require all the superconformal transformations to work with the Youngian symmetry, and if you want to do that, well, if you never work with superconformal boosts or conformal boosts, that's going to be quite a mess. So it's actually best done in superspace. And then this was done by, well, not in full superspace, but the calculation, well, indeed in full superspace, but in expansion. By this group of people, the Youngian symmetry has been demonstrated at the first few leading orders in theta. However, there were some subtleties regarding the boundary terms. That's the motivation for the first part. So let me just explain what this Youngian symmetry acts on the Wilson loop. First of all, how conformal symmetry acts, because that's part of the Youngian. That's the 0 del fragment by the structure constants, and that's sort of what the Youngian gives you.
But you can also add the local term.
I can also add a local term, but I'm not yet there. Now, the Youngian is then, this is just the action of the operators. It's a symmetry if the expectation, the transformation of the expectation values vanishes. Normal symmetry is usually this statement, and the Youngian symmetry is if you have this in addition. So it's just these two statements you sort of need to prove. And then all the higher levels of this infinite dimensional algebra in principle follow from these. There are certain difficulties. Well, first of all, it's not really clear, or wasn't really clear, how to compute perturbative corrections. And then next, we also need a precise definition of this finite Wilson loop, how to actually make it work for all of this in theta. This was in principle clear, but you have to work out the details, of course. How can you then act with the superconformal generators on this object? And finally, how you define the Youngian. That might not be a big step, but this was actually a problem. Now, the next thing is about the boundary terms. So there was some problem with the boundary terms, and we had to solve this problem, how to really incorporate the boundary terms correctly, and that's related to actually defining the Youngian action, and I'll talk about that later. Well, how about regularization and local terms? That was already mentioned. We do need some local terms to make things work out. Is the action actually consistent with the constraints of this, say, 10D light tightness? And does the Youngian algebra close the one that we define with the particular representation? Does that close properly, and how does it close? Now, okay, so let me start by talking about the Wilson loops in superspace. So first we extend the ordinary spacetime to a superspace, and with that you can easily define any two small superspace mills on the superspace. Extend the gauge potential to all these superspaces. But if you just look at the fields, then you have all the theta expansion components of the gauge field. There's way too many component fields for superspace mills. So we need to impose a constraint. And actually there's a set of 3 simple constraints that you so we fix some of the components of the field strength. We say this sort of mixed chiral contribution in the fermionic directions of the field strength is 0, and the other 2 are related to the scalar field, the chiral ones. And if you impose these constraints, actually by Youngian identities, you find a couple of other constraints, and these define, for example, the fermionic fields, psi and psi bar as the top components of these parts of the field strength. But also they imply the equations of motion, which makes it a bit complicated. Now, however, you can quantize this theory and actually derive a gauge propagator from the equations of motion, and you can also derive other propagators, say mix a scalar gauge field propagator, which actually follows from the fact that the scalar field is part of the field spectrum. So everything follows essentially from this gauge propagator that we needed to find. And in particular for the Wilson loop, that's all we need. So let's first generalize this Wilson line in the space. So here, this is the ordinary Wilson line. Here you couple the gauge field to the super space field line, and you couple the fermionic components to the fermionic directions and then the scalar field. And so then the Wilson loop expectation value at the first non-trivial order is just where you insert the propagator between 2 points of the Wilson loop, and that gives you the full answer. So we don't actually need to deal with interactions and vertices in this theory at this one loop order, but we only need the propagator. We also discussed a bit of kappa symmetry, which is a different name for local fermionic symmetry. So if you have this path like in 10 dimensions, then in addition to path reparameterization, you get 8 local fermionic symmetries, and you sort of get an extended path reparameterization algebra, which is 1/8 dimensional, and which in some sense makes the path fat, because you can shift the path a little bit to the sides in the theta directions, and don't actually change anything about the expectation values or the definition of Wilson. Okay, in order to make this work, you only need this one bosonic constraint element, and you expect that things are fine. Let's check this. Actually, this 1 over epsilon part goes away, and secondly, if you add the scalar propagator to make the path dimensions, you find another 1 over epsilon squared divergence with a different prefactor, and remaining propagators that we also need are non-singulars. We don't need to worry about them. But if you add everything up, it turns out that the singularities cancel if the path is null and empty, because this term here cancels against that term when q squared is the same as p squared. And also, this is just a derivative of the same condition. So, this is indeed the 10 null means that that Wilson is fine. Okay, so let's then continue with the symmetries. So first the conformal symmetries. So you again have this one loop expectation value. For the conformal action, you act with the conformal generator on this propagator, which has 2 gauge fields. And what you need to do is you need to act with this generator of gauge fields and then compute the expectation value. So in some sense, you're computing this new Wilson loop where you have 1 gauge field and 1 sort of shifted gauge field. And the result of that turns out not to be exactly 0, but just a total derivative, which is fine because once you insert it into the Wilson loop, you sort of get 2 total integrals and they integrate to boundaries. And then actually the 2 boundaries cancel against each other, one with the plus, one with the minus, and then things go away. Actually, this here is not quite surprising because this is a gauge transformation, and because you're quantizing the gauge field, and the gauge field is not, transformed like a gauge field, but not covariantly, and so you actually expect some total derivatives to appear. Some of these terms are actually 0. That is for the manifestly realized symmetries, which are preserved by the gauge fixing. But for others, like the special conformal transformation, these non-trivial derivatives. And what's important and nice is that the remaining function f12 here is finite when you go to the limit 1 to the ultraviolet limit. And that's nice because then all the divergences cancel. That. Okay. So that settles the story for the Wilson loops. We now have confidence that we can work with these objects, and let's now consider the Youngian invariance of these guys. Okay. So there's always one particular generator of the Youngian symmetry that's easiest, and then that's usually the level 1 momentum, or the so-called dual conformal generator, which I'll denote by p hat. And it's a bilocal insertion. I'll just write this as a bilocal insertion of 2 two conformal transformations, which consists of nicely just of the ordinary Poincare transformations and scaling transformations. So you only need the momentum, the dilatation, and the rotations, and the supercharges. And so this is actually a nice thing because it might also, this type of symmetry might also generalize to theories where you only need to supposed to generalize. Where you don't have conformal symmetry, but you know, otherwise you need to go conformal anyway. So now I'll show you how to act with this operator on the propagator. We can actually act on the propagator and then insert that into the Wilson loop. So you sort of need to act on these two gauge fields with the two conformal generators contracted by the structure constants. And again, if you do that, you can show the result should be a total derivative in leg 1 or leg 2. Unfortunately, here, if you compare it to this expression, it's almost the same, except that there's a minus sign there. And that's really unfortunate because there's an ordering issue, and the minus sign really needs to be there. It's not an artifact, it's just because the Yangian reverses parity. And then it turns out that the boundary contributions do not actually cancel out, but they sum up. And if they sum up, then you have to deal somehow with the boundaries. So, well, as I said, it's almost zero, but yeah. You can actually work this out, and then most terms go away, but there are some odd boundary terms which remain, so that you sort of have to open the Wilson loop at some point, and you will get some residual term at this point, and this is something you really don't want. You really want to have this canceling. It's not really clear how to compensate for that. You could invent something, but that not work out. However, there. Well, let's be simple. You can, but maybe later. I'm not sure if finiteness, actually all this finiteness issue is probably not one of the issues, but you can talk about this later. Yeah, but thoughts evolve, and it's try to be simple. You can probably discuss intersections, and then you may think about contact terms, but I can't really say anything. But there are actually some two fundamental problems that we also discovered when acting on this in this way, because the definition that we have is actually not cyclic anymore, and it's also not gauge invariant. And so what it means is you have a gauge invariant operator, which is the Wilson loop. You act with this symmetry on it. You get an operator which is not gauge invariant, and that really means it's stick. You shouldn't look at this because you're looking at gauge theory. Anything that depends on the gauge degrees of freedom should not be physical. So if we have, this definition is in that sense not physical. However, there is a resolution to this. The point really is that this insertion where you shift the gauge field by some amount is not gauge covariant. Essentially, like the gauge field itself, it's not gauge covariant, but you can actually rewrite it in a nice form. So you can write this shift of the gauge field as something that involves the field strength and the total derivative, gauge covariant total derivative. So the nice thing is this term here is covariant, and the second term is a boundary term. And the boundary terms you can usually discard from those groups. So the proposal is, let's just drop this derivative term, forget about it. It doesn't change anything about the conformal action. So you now define the conformal action to be an insertion of this operator rather than this one. And of course, for the conformal action, nothing changes because the only difference is the total derivative, and the total derivative integrates to 0. So that doesn't make any difference here. However, there is a slight problem because now we're sort of mixing up the conformal symmetry with the gauge symmetry, and so the closure of the conformal algebra is just, this is the ordinary closure, but you also get a gauge transformation, and the gauge transformation involves the field strength of your here. Anyway, so there's this particular combination G and N of fields, which involves them. But it's just a gauge transformation, so here at this point it shouldn't really matter. But we can now do the same thing for the Yangian, and because we now do two of these insertions, then there's some interaction between these two boundary terms, and then that makes a difference. And that actually resolves both of these problems. We now have a fully cyclic definition and the fully gauged invariant definition because we only use the field string.
Sorry, what is capital X?
X is the position. It combines the bosonic and fermionic directions. Okay, so indeed you need a curious identity to prove the simplicity, namely you need that the commutator of true conformal transformation contracted with structure constants is 0. So this actually boils, if you look at this algebra statement here, it boils down to this and this term being 0. So this term here is 0 because the algebra, the conformal algebra, is equal to 2.2/4 and it has vanishing to a Coxeter number, and that's what should appear here. And the other thing is that the structure constants contracted to this field G turns out to be 0, which is quite a coincidence if you wish, but it's a very nice feature which is true for any two spores with variant. I'll mix it up with the gauge transformations, and we don't really know how to do this. However, all the residual terms that you find in the algebra, you can now, not quite, but this is all sufficient for the invariance of the Wilson loop. So you now have a definition of the Young action which may in principle annihilate Wilson loops. And let's prove it. So this is nice to act with this mu generator on, let's not act on two gauge fields, but let's act on a derivative of a gauge field and another gauge field. So this is more or less the field strength, but we're now looking at the linearized theory. This is sufficient for one loop. So let's look at that. So you act on this. One is the field strength, and the other one is the gauge field. But now what you can do is you can do a sort of partial integration. You can take this operator Jn and pull it out to act on everything here. You make it act on okay. Yeah, no, I don't know. You can make it act on these two fields, but of course that's not the same as this, so you remove the actual term. It's just like you treat this J as a derivative operator and you do partial integration. So then you've rewritten it as two terms. Now, the nice thing about this term here is that here you've produced, out of the gauge potential, you've produced a gauge covariant operator, or gauge invariant operator now, which is the field strength. So here you get a correlator of two field strength. And the nice thing about that is that it's gauge invariant. And once it's gauge invariant, it's annihilated by the conformal generators. So this means this part here is 0. Now the second part is also 0 because of this identity that I mentioned. Because here you get a commutator of two conformal transformations acting on A, and that's contracted with the structure constants, and that's 0 for me, also written down. So if you put this together, it shows that the action on the gauge propagator here must be a total double derivative because it has to be this, because once you hit this guy here with a total derivative, with an exterior derivative, this must be 0. So that's sort of what the only thing you could possibly have there. And you can also compute it explicitly for the level 1 momentum operator, and you act on this chiral propagator, you get this particular combination, actually with two derivatives, one on each of the two fields. And also for the scalar fields, you also get 0 right away because the scalar fields are part of the field strength, and once there's a field strength in here, it's already 0. So the point is that now when you act with this generator on gauge propagator, you get a double derivative contribution, and if you act on anything else, then it's 0 right away. So, and that you can now insert into the Wilson loop. So you insert this double derivative operator into the Wilson loop where you integrate over the 2 points in an ordered fashion. That's what you need for Youngian. So because there are derivatives, you can integrate things up, but you will end up on the boundary. And there are two types of boundaries. There's the boundary sort of where you cut open the Wilson loop, and there's the boundary where the 2 points collapse onto 1. Now it turns out that this here, because there's another derivative left, this is the boundary contribution where you cut open the Wilson loop. This one turns out to vanish because there's another derivative that integrates to 0, but the other term just remains. So it turns out that there is a residual contribution when the two insertion points go to a single point. But that's nice, that's also what Kostya mentioned, there can be some local counter terms, and you can use these to remove them. So we define now that Yannian level 1 action on the Wilson loop as a local action, plus, as this bilocal action that I discussed, plus a local term where you sort of hit this level 1 generator directly in the HTTP. And for that, we haven't made any definitions yet, so we basically just define this to cancel off this term, and then we're fine. And so that means the Wilson loop expectation value at one loop is actually Yannian invariant. Well, this was a little bit too fast because there are regularization and renormalization, namely because this term, well, it's not just there, but it's also infinite. It's actually quadratically divergent. So if you look at this, you can extract a quadratic divergence, cutoff parameter. And somehow you need to renormalize the local and boundary part of the Yannian action, but that can also be done. It's just, you have to be careful. You have to make sure that you can remove the 1 over epsilon squared and 1 over epsilon divergences, and then you're fine.
How is the original expression finite, and you act with some symmetry and you get the divergence before?
For the original action, the remaining term is actually just fine. But here, you see, you start with a double derivative. Now, if you have something, a propagator which is 1 over epsilon squared, and you hit it twice with the derivative, it will just be more divergent.
I'm just thinking, suppose I forget about some diagrams and I just have the result. Some functional of the loop and it's finite. And now I just change a little bit the contour and see how this finite result changes. How could I generate?
No, but you change the contour not globally, but by 2 points independently. And the 2 points that you're changing is actually the 2 points of the Yannian insertion and the 2 points of the propagator, and then you get divergence. It's a simple package.
For example, for a circle, this amounts to putting 2 small bounds on 2 points of the circle.
Yes.
And this is when the 2 bounds are close together, so you get divergence.
Yes. Because it's not that you're not shifting them in the same direction, you're shifting them in different directions. And each shift gives you a derivative, and what's 1 over epsilon squared is now 1 over epsilon to the 4th, and then maybe it gets some magic, but at the end it's still 1 over epsilon squared. But it doesn't matter because I can just remove it by this local term. That's what the local term is good for. So what does this imply for Yannian symmetry? So what do we learn for Yannian symmetry? Well, it's still invariant. We've just done it in one loop, but order g squared. But what happens at higher orders? Does it still apply? Also, is this the only invariant object you should look at? Are there many other objects that you could look at? Could we somehow prove this Yannian symmetry in more general? When you think about these questions, then in particular how to make things work at higher loops, you need vertices and think about it. And what we actually need to show is that J hat annihilates S. And in this case, S is actually not the scattering matrix, but it's rather quite an embarrassing statement because what I mean here is the action. So what we should actually show is that J hat, the Yannian generator, annihilates the action, or in other words, the action is Yannian invariant. Now, this would be nice. This is the project we're doing with my student. So we want to show Yannian invariance of the planar action. And the first question, and that's actually quite an old question, is how to apply this Yannian generator to the action. I mean, first of all, the action is not really a planar concept. How can you act on this action by discarding the non-planar contributions? When when I thought about this some years ago, that this was not really clear. And also, what representation should you take, and how can you really should you use computing? Off-shell or on-shell, yes. But this also here, this investigation gives you some hints. Namely, what we've seen is the propagator is the Young invariant. This Young invariant may be up to some gauge artifacts, but it is well linearly invariant under that. So that's nice. If you and you can also think, if you think about Wilson loops and maybe you know about lattice gauge theory, then you define the action of lattice gauge theory through a Wilson loop. So maybe the Wilson loop should actually contain Lagrangian. So somehow maybe this Wilson loop invariance tells you something about the invariance of Lagrangian of the action. And after all, the Lagrangian is just a sequence of fields, and the Wilson loop is also just a sequence of fields. Okay, so not a discrete sequence of fields, but you integrate the fields over the path, but still sort of the same type of object. So this means we can actually use the above classical and nonlinear representation to act on the action. And there are some essential features of the action that are quite important for that. And one is, well, the action is single trace, so it doesn't have a disk topology. You can take a large n limit of it. The action is conformal, so you can, it's conformally invariant, and that is required to make the cyclicity work out, and also the action is not renormalized, so that maybe gives you hope that there are actually more anomalies for this solution.
It is wave function normalized.
Yeah, but wave function renormalization is something you don't really need to care about. This is something for the internal calculation, and things always cancel out. And as I said, there are some renormalization issues, but at the end of the day, there are no 1 over epsilon terms that you need to get rid of the violation of symmetries. So, to apply the Young generator on the action, that needs some care, but so we started with something simpler, namely the equations of motion. Let's add on the equation of motion. This is certainly something you need for consistency. For example, if you use the quantum formulation, you usually work in some sense on-shell formalism, so you better have that not only the equations of motion are sort of zero, but also the Youngian acting on the equations of motion just produces more equations of motion. This is just consistency of constraint. And then let's just look at one equation, namely the Dirac equation. The Dirac equation is d psi plus phi psi to the power term equals 0. And you can now act with this j hat bilocally on this thing. Now, the bilocal thing here applies to the color space. So all of these guys are matrices, they have a particular ordering, and the Youngian needs to know about this ordering so that it can hit the individual terms in the proper order. When you act with that, you actually, from the covariant derivative, you pick out the gauge field, you act on the gauge field, you act on this, and here you have a quadratic combination, so each of these things acts on a field. And then you have to realize that such a commutator is turned into an anti-commutator due to the parity inversion nature of the Youngian. So if you look at this, then actually many terms cancel. However, some terms that you get do not have counterparts. You have to be inventive to remove those. So how can we make the equations of motion invariant? Well, we haven't yet specified the action on single fields. For the one loop we have, but for this classical discussion here, we can actually act on single fields and say define that the dual conformal generator acting on a gauge field gives you a combination of two scalar fields, all the indices work out, and also acting on a fermion would give you an anti-commutator of a scalar field and a fermion field. And then this turns out to be 0. And these would be precisely the terms you need to remove all the terms, and then the Dirac equations can And we've indeed shown, with this definition, we've shown the invariance for all equations of motion, for the scalar fields, for permanent fields, for the Mills equations. And we've also, also the other Youngin generators, not just the dual conformal generator, they in principle follow from the algorithm. We know how the J hats commute with the J's, you can make statements about the other generators. So this feature that you get anti-commutators, that's quite in line with the odd parity of the Youngin generator. Now, all these terms that I put here, you might wonder, does that conflict with what I told you in the first half of the talk? And not quite, because this is a bilocal combination of the fields, and you wouldn't simply see it at one level. All the terms wouldn't. This would be a higher order term. This is only maybe the local counter term could get a contribution, some divergent contribution from here. That's nice. That would be nice. It doesn't. The numerical coefficients here do not quite match up, but we have to check that detailing. And in any case, you can always add numerical terms to. This is just going to be a shift of the numerical terms, so it's not a problem. Okay. So next, we want to show the invariance of the actions. The action is the integral of the Lagrangian, so which means we should show that J hat acting on L is a total derivative. It doesn't have to be zero, it just has to be a total derivative. There are a couple of difficulties. First is, maybe foremost, is IGST. Where can you cut open this trace of the Lagrangian? Conformal symmetry should in principle help. The Lagrangian is conformal, so you should be able to cut it open at any point. But there are now different terms. There's the kinetic term for the gauge field, for the scalar field, there's the interaction terms, the phi to the 4 term. You can cut them open at all different points, and then that would, in principle, give you different results. Anyway, so it's also not so easy to do this because you actually get quite a few terms from this. It's not linear. You have to deal with the spinor algebra. Should be used the equations of motion. Well, we intended to do it with all possible orderings, but that didn't work out. The ordering issue persists, and the result does depend on the cyclistic representative. So again, you have something that depends on the representative of an equivalence class, and that is not a good definition. So it's probably the wrong approach. So would remain how to cut open the trace of the action. There you can again take some inspiration from the conformal symmetry. So again, let's just write the conformal symmetry acting on the Lagrangian using variations. So you vary the field phi, and you vary the field d phi. Phi is just a blanket notion for all the fields. And this is just elementary Noether mechanics. So these are the two terms. You do a total derivative. So this you then get this combination where you act on the field times the equation of motion. And some overall fields, that gives you zero. That's indeed true. The result is zero up to cyclic shifts and total derivatives. That's the statement of conformal symmetry. And in particular, we don't need any equations of motion to show the statement. This is, if you wish, a Greek and off-shell symmetry statement. Otherwise this would be a trivial statement because that's the equation of motion, and that's zero. So we must not use the equation of motion for this. But the nice thing is we can generalize this to the Youngins. The first variation, we now say let's let the first variation hit the first leg here, and the second leg of this Youngin generator hits the equation of motion, and that's here. We just insert another generator here. And the question is that zero, and indeed it's zero. You don't need the equation of motion. Also don't need a local term, so to understand how that comes about. But indeed, this whole combination is zero. So you have some symmetry generator acting on a field, and one on the equation of motion. You sum everything up. Gives lots of terms, but they all cancel. Okay, actually I can prove this. This is actually a very easy proof, so let's just denote d phi as the equation of motion for phi. So d phi equals 0 is the equation of motion. So let's act with j pull, let's see, I pull this this thing out of the bracket to make it act on both things, and I subtract what I did wrong, and then you see, well, there's this term, but this term here, what's in here, is all already invariant by the equation of motion for the for conformal action, right? This is due to conformal symmetry. This is 0, and this part here is 0 because acting with these two fields on phi is 0. There are some subtleties which I just realized that one has to be careful about this. But I think this is pretty much the same statement as for the Wilson loop, so I think it makes sense that you get this estimation to work out. In any case, we showed it for the dual conformal momentum, that all of dual conformal symmetry, that this is 0 indeed. So, but it's not quite clear how this relates to the equation of motion. Anyway, we now have a proper definition of integrability for n equals 4 square mils, and indeed n equals 4 square mils is integral by this definition.
At the leading order.
Pardon?
At the leading order.
Pardon?
It's an order.
No, not at the leading order. It's an exact classical statement. And so it's exact classical, it's not units, and you might wonder about quantum effects. But we know, well, what we know is that Lagrangian is exactly invariant. So that I've just shown. Propagators that we've discussed, they are linearly invariant. Propagators are sort of 1 over L0, where L0 is the free part, not to gauge. And the interaction vertices, if you put things together, should not be invariant because this is just linearly invariant, this is exactly invariant, so the difference should quite be invariant. But if you combine Feynman diagrams from these ingredients, you should again recover invariance. And the idea is sort of, if you have, say, this Wilson loop with some interaction vertices connected by propagators, then you can shrink this this thing that defines the Yangian to go around the vertices and go around the propagators, and then there are some violations of invariances, but they should cancel between the different diagrams that you need. This sounds a bit like magic, but that's how usually symmetries in quantum field theory actually work. So we do have exact classical nonlinear symmetry, and I say this is sufficient in the conformal case. Maybe one derivative by lambda computation to obtain loop effects. So if you take a lambda derivative of a correlator, then this is the same as inserting a Lagrangian into this correlator. And for the large n limit, it means that you sort of always need to insert these actions into the area you're already considering. You don't want to open up new handles and so on. So then, if you have this, then actually the J hat annihilates each of these vertices precisely, and that maybe brings you a little bit closer to that statement. And in any case, the equations of motion do hold in quantum theory. You might know them as string Dyson equation, but these can also be used in the context of symmetry. So the only question that really remains is, are there quantum anomalies? And of course, conformal symmetry is usually quantum anomalous. But unfortunately here how to deal with these anomalies, because the action of your Yangian is non-local, certainly non-local in color space, and that might be a difficult part to implement, but maybe also in space-time. And well, the question is, how can you treat the violation of these non-local currents, and what's the proper homological origin? But, well, we know for sure that it's not an issue for the Wilson loop expectation to have value at one loop. And also, one thing we know is that the anomalies come from an interplay of the symmetry deformation by regularization. If you regularize the theory, you deform the symmetries, and you also introduce divergences. And if somehow the divergences balance the deformation of symmetries, then you get anomalies. However, here you effectively don't expect any quantum divergences, and therefore you don't really expect anomalies. And we've seen enough evidence that actually there's probably no anomaly. Not a weak coupling, not a strong coupling. So let me skip that and come to the conclusions. So I've discussed modest linear Wilson loops. We've written down a proper definition of these modest linear Wilson loops in this full superspace, with which we can work with, and we can also show the finiteness and almost at the first loop order. Then we've discussed Youngian invariance of the Wilson loops. We've shown how to act with this Youngian on the Wilson loops to recover all the nice features. And we've shown that the Youngian is a symmetry of the Wilson loop expectation value at order g squared. Finally, we've discussed Youngian symmetry of any equals Sophia Mills. We've shown that the equations of motion and the action are both invariant as far as we can define this anyway. And thus, n equals post-Sophia Mills is actually integrable. And I would say that I don't expect this would happen.
Okay. Well, anyways,
so you after.
Two questions. First, about the first part. Don't you need a Wilson to couple off-shell fields where walk pseudospace?
I'm not sure I can understand you.
You mentioned the constraint equation when you walk in pseudospace impose the equation of motion, but you would like beyond leading over the Wilson to couple off-shell.
Sorry, I still didn't get it.
So definition of the Wilson loop in pseudospace? On shell.
Yeah, I mean, the Wilson loop, if you wish, the superspace, what's the proper statement? I mean, what people say is that the superspace is on shell, but it's more like the gauge theory formulated on the superspace. You need to impose the constraints to remove all the unwanted degrees of freedom. And indeed, the equations of motion are invariant, so there's no problem with that.
But the definition of the Wilson loop is off-shell.
Yeah, no. I mean, this is the usual. You can. I mean, all this. All the operators that you write are on-shell operators because that's the only thing that you have.
Maybe we can discuss this later. The second question is: don't you expect anomalies from the boundary of one-like space, meaning when you have self-intersections or develop casts?
Sure, but that's not the theory. That's something you put on the theory. If you want, I mean, if you want to compute the Wilson, the Youngian invariance of the car, then you have to first define what's the car. And the question is this car compatible with all the definitions of the car? But this is not a question of n equals supposed to be or not. Or for the Wilson loop, of course, I mean, yes, if you have, I mean, the assumption here is that the Wilson loop is smooth, it's non-null everywhere, and it doesn't self-intersect. If you want to do any of these situations, you're invited to do so. And if you have a corner, that will do something. If you have Wilson being null, that makes some problem. But we just try to look at the generic case where we don't run into these problems.
If you wanted to use it to solve for the Wilson loop, you better understand its points. The symmetries to integrate them. Maybe we can discuss it.
So if I understood you correctly, the first bullet point, the equations of motion and action and invariant, is not a large n. Is that correct?
This is a large n statement. The equations of motion are invariant in the large n limit.
When did you actually use large n in that case?
Well, the point is, okay, you have the equation of motion. Let's look at the scalar equation of motion because that's something like d squared phi plus phi cubed plus psi psi is 0, right? So there is an ordering of the three scalar fields. This is done by a double commutator, and that gives you a particular ordering, and the point is you need to act with Youngian on this particular ordering to make things work out right.
May I ask? Two questions. First, can you write those equations here? And the second question, you know, those equations in the old sense, and what is locality here? What sections?
You're much more an expert in loop equations than I am, so, but I think loop equations is all about self-intersections, and so I don't know, what do you want to do with the loop equations?
Because it's a closed equation, it does use the action of the theory, so it could actually prove the Youngian symmetry of the action.
Yeah, but you know, you can also just use the classical action and prove that.
What?
I mean, you can just use the classical action and then be happy with that. Or use Schwinger-Dyson to make it a proper statement.
On this also.
I mean, isn't the loop equation more or less a Schwinger-Dyson equation? Or
Yes. But it's geometric. It's geometric. You deform the loop, etc. This is the whole point. Can you do it in geometric way here? That you deform the loop and you.
Yeah.
You
I mean,
can.
there are many things you can do. As I started with this talk, there are many definitions of integrability you're invited to look at in various forms.
Okay, second quick question. Do you know how to define the disk partition function of the side state in sigma model to define this loop? What are the boundary conditions on the field to define such a loop?
I don't know. This was a purely case view.
There's workload.
Okay, last question.
What about, in the third part, what about gauge fixing, the arguments? Did they involve some kind of gauge fixing? I think you had some slide which.
Yeah, I do have some slide. Of course, I mean, if you want to show consistency with gauge fixing, you would typically look at IGST symmetry, and I'm not entirely sure what to do there, but one problem is that IGST symmetry is a field-dependent gauge transformation. So gauge transformations are good, are fine for the Youngian because the Youngian maps the gauge invariant operator to a gauge invariant operator, so it doesn't introduce any. Now, the problem is if you have a gauge transformation which depends on the fields, then the fields carry some momentum, so they inject momentum into your Wilson loop or other thing. And once you have this momentum in there, you don't have conformal invariance, and then it's a bit unclear what to do. But I think the statement is that IGST symmetry makes sure that all these unphysical degrees of freedom don't really surface, and also the Youngian does not introduce them.
Okay, really fast.
How this connects to the statement about invariance of generating functions? The statement about invariance of generating function for the amplitudes, for real amplitudes and the Youngian symmetry, because the action.
Well, I don't know.
Morally, the
At this
action.
point, I refuse to make statements about scattering amplitudes because they are divergent, and I really don't know how to deal with those divergences. I think one can make statements, but I think they depend on the regularization eventually. And I try to do statements without that. But yes,
An action, the action has a meaning as generating function for the amplitudes. That's true level.
the action is a generated function.
Yes, evaluated on a solution in
There's the effective action.
no, it's a classical action. But real level amplitude. Yes.
Yeah, but three level
Your statement is
amplitudes are all invariant.
yes, but your statement shows that real level, the invariance of the action.
certainly tree level, but as I said, composition shouldn't really introduce any trouble. There are various ways of combining the IGST generators to avoid all this complication.
Okay.
Sorry, you want to get past? Sorry. should maybe. Mr. Sa- was the theater?
It was really good. Seats were, how should I say, they optimized the space. It was really nice. So the play was nice and the atmosphere was cool. So yeah. How was the public lecture? Did any? Was there?
It was successful. A lot of people showed up.
Okay.
There were, well, I would have liked it there to be more young people,
Oh, okay, yeah.
but there were a few.
Uh-huh.
One of them asked Jan, how does string theory solve the problem of inertia? And then Jan he didn't have a quick
Because the question, what problem would have been bad?
yeah.
I was asking, how do you compute mass renormalization in string theory? That's an interesting question.
Yeah, I see the latest papers by Sen.
Yes, exactly. That's a very interesting question.
Of course, there was the guy who asked about background independence.
Of course.
And, yeah, but it was fine.
Okay. I mean, the question about background independency, you were ready. I mean, you knew you were, it's not a problem. I'm puzzled. I'm puzzled by Nicholas's talk, but okay.
Actually, one thing I find puzzling is that you have these SUN fields in the left-hand side, you actually Yangian on them, and then you get anti-commutators, which have traceless. So you produce traces out of traceless things, and not necessarily. This makes me a bit uncomfortable. I mean, usually all these symmetry operators they leave you in the same sector. So, yeah. Maybe Niklas would say there's no problem. I'm not saying there is a problem, I'm just saying this makes me a bit nervous.
Yeah. I also don't quite understand the discussion about planarity, but
That's why you have commutators all the time. I mean, all of these,
yeah,
they produce commutators or single fields.
yes. That's. I guess it's my problem, so. At what time are we leaving for the walk?
So, 2:30. I hope it's gonna be okay.
Should be.
It's not drizzling or anything.
No. But where from? From
From front of the college.
front of the college?
Yeah.
Street side or inner courtyard?
I'm gonna meet the guy in the lobby.
Okay.
So,
Do you know how many people sign up?
12. This is pretty bad. I'm trying to get somebody to make an announcement to boost the numbers. I mean, it's not. So, Niklas this morning wanted to give his talk on the Raspberry Pi.
Seriously? He did that. He told me he wanted to.
It didn't work.
Really?
No.
He told me he wanted to program the Raspberry Pi so that it would automatically boot the talk.
But it didn't work. No image appeared on the screen.
I see. So you were safe.
Of course, now probably he's debugging it.
Yes. But did he give you a good reason? But for because I can? Okay.
All right, so my great pleasure to attend this conference, and let me, I would like to thank Renato for this kind of invitation. This, my talk is based on the joint work with the Volodya Bajan and Lev Katalusov, search the formal title, but in fact I would like to use this opportunity to discuss some approach to exact solution of integrable quantum field theories, and the most part of my talk will be actually more quite general. This approach, I would call it correspondence between correspondence between integrable quantum field theories and differential equations, maybe either ordinary differential equations or partial differential equations. I will going to talk about evaluations in Okay, and let me first start with some baby version of this correspondence. Actually, the correspondence between the quantum mechanics, quantum mechanical systems, and classical systems. So here is the problem. So the problem is going to be the particle just a Schrödinger equation, quantum mechanical system, particle in and this potential, post potential, mathematical is usually referred as a modified equation. Okay, and this is combining potential, so it looks like this, the profile of this, and there are only this component in the spectrum. And the potential depends on parameter q, and as the q goes to 0 for small q, it's very easy to understand how the spectrum of the particles looks like. Indeed, as the q goes to 0, then we have the potential flat, right, just this. The segment, the length varies almost 0. The size of the or is proportional to logarithm 1 over q. So basically, in the rough approximation, the spectrum defined by the same quantization condition as a particle in the infinite. We can take into account the corrections, and correction comes from the reflections of reflection on the exponential variable. And as for sufficiently large pi, cost can be replaced by an exponential. In this case, the equation is actually form of Bessel equations, and if you immediately calculate the reflection amplitude on exponential variable, it's given by some ratio of gamma functions. And including this phase shift, we have 2, because two sides of the potentials, and in the leading approximations, when q goes to 0, the Merkel consideration condition can be written this form, which defines the spectrum. Approximations, it works pretty well with sufficiently small q, but it can be done more accurately. Actually, the exact Merkel consideration condition. In this case, you need to include additional terms, delta here, and which is expressed in terms of function e and some function e, which depend on e. And the energy, so this is a formula which defines the spectrum. And the function e, it can be systematically expanded in power series of q. In fact, here is r, but it's actually the square root of q, 4 square root of q. And in principle, this function can be calculated, and it's a solution of so-called transcendental equations where e is a famous Hill determinant. Okay, so this is a quantization. In principle, this functions, all this function e, this functions e is implemented in Mathematica, and you can calculate the spectrum, well, just in a few lines. So define the whole energy spectrum for this potential. All right, and that was this is the story of the classical part of the correspondent, quantum part of correspondent, quantum mechanical particles. But now I'm going to the classical part, and I will here we cover classical equations. I mean, I call it classical, but actually in the three equation I call it classical because this equation in proper coordinate, this equation can be, it's a pendulum free equation, it can be written Newton equation with a time-dependent potential. So we can think about this equation as a certain Newton particles, classical Newton particles, and that will be the correspondent between the quantum mechanical, the correspondent between quantum mechanical particles and the classical particles, which is described by the Newton equation. But in the three equations nonlinear equations, and some special property of the singularities. And it is known that all singularities or singularity of the solutions of this equation can be classified, in particular the possible singularities are so-called movable double poles. So the solution can be local solution can be presented in Laurent series expansions with the double pole. This coefficient is fixed by the equation. This coefficient is also the residue also fixed by the expansion. And in principle, you see it's families. So general solution of some kind, because we have a parameter r which is fixed, which is shows position of the singularities, and we can use also as an independent parameter the regular term in the expressions of the solutions in the Laurent expressions. Actually, it would be convenient for me to use the parameter r, which is actually the same, more or less the same description. So this is a movable singularity, but also there are two singularities at t equals 0 and t equals infinity. As t equals 0, it can be either the solution, either accumulate this accumulation point for second order poles, or another possibility that is some power law behavior. At t equals infinity, again, there is some in some cases, in general, it would be accumulation point for second order poles and 0. But also there is another situation, some special solutions where actually the limit as equal or plus infinity exists and equal to 1. It's another thing. So this is more or less descriptions of the singularities. And now, so we can consider the following problem. We can consider the solutions which would meet the Laurent expansion at the point r, and now let's try to adjust the coefficient a. So the regular, so the constant term of the expansion in such a way that the solutions has exactly n double poles on the ray where t greater than r, and finally it has only poles, and finally it has a limit at t goes to infinity and limit to 1. So it's rather special, it's rather restrictive conditions, and actually specified the solution unambiguously. And my statement then, but it's required, of course, adjustment of the coefficient a. And the statement, the relation, correspondence is the following. So if we identify r position of pole with the parameter of infinity-Gordon potential u in this way, and then an after sign would coincide with the eigenvalue. So you see that you solving the classical Newton equation somehow. If you can construct the solutions, you can solve the quantum problem. So this is a smell of correspondence. And now it's interesting that these relations between the quantum mechanical systems and classical systems can be generalized for the integral quantum field theory. And let me describe it. And the generalizations, let's start with the quantum side. So the unified Mackey equation we replace by Sinch-Gordon equation. That this is Lagrangian. So now it's the field phi depends both on time and coordinate. We consider we impose the periodic boundary conditions. So we put the system on the circle circumference r, and then for example we can address the questions of ground state and energy as the functions on the circumference r. Right? And here but this is a quantum field theory problem, 1 plus 1 dimensions, integral models. But still, when r goes to 0, when and short distance limit, we can slightly work the quantization conditions for the Mackey particles, modified Mackey particles, and write the quantization condition in a similar form. So basically, it looks like a mini, usually referred as a mini superspace approximation to the problem. When we replace, we ignore the dependence on x dependence and just leave the t dependence and well reduce the problem to the quantum-mechanical particles. So it still we have a similar quantization condition, but now the one modification is useful here. We need to replace delta, which was, remember, that was a phase shift, which can be obtained through the solution of Bessel equation. We replace it by so-called fluid reflection amplitude. So this is the result in quantum reveal theory due to such analysis of homological. And once we replace quantization condition, make these modifications, you see B is a coupling constant, and when B goes to 0, this part is disappeared and we return from the mini superspace amplitude. But with these modifications, actually, these quantization conditions work pretty well, and it was demonstrated in the original work of such analysis. So, but of course, this is a quantization conditions for short distance. Okay, and now, so this is a quantum part, and now let's discuss the classical equations. Again, I will just take some manipulations with the Pindevet 3. And first of all, let me know that the Pindevet 3 equation, this is a standard canonical form of the equations, can be written in this form, in the form of Singe-Gordon equations, once we assume that this is partial, but once we assume that solutions depend on consider the only radial symmetric solutions of the Singe-Gordon equation, then these equations, the choice of solutions could be, we need another solution of these Singe-Gordon equations, and it can be described as follows. We have to consider the systems on the domain, which is shown in yellow. It looks very quite strange. It's a combination of certain ages, and this age is defined by the coupling constant. As you see, this angle is roughly 90 degrees. And so you should solve the, of course, the solution, if you consider the Singe-Gordon equation in this domain, the solution would not radial symmetry because the domain has no insymmetry. But nevertheless, you can consider the solutions with certain boundary conditions. Also, this edge or these arrays should be identified, so we can pose certain periodicity conditions for the solutions. And the solutions exist in unique. Once you solve this equation, for example, numerically, calculate this integral, and the statement which was in our work with Sasha homological, that this integral actually gives the energy on Singe-Gordon theory, and remarkably that the classical systems we see, this is classical partial differential equation, but the quantum, all the quantum information theory, for example, about the coupling constant hidden in geometry of this domain, right? So in particular, from it's clear that if you substitute B to one of the B, the domain actually creates this kind of symmetries, and the energy remains the same, so it manifestly leads to the self-duality of Singe-Gordon equations. So the coupling defines the geometry of the domain, and the overall size of this domain is controlled by the so-called measured in the unit of correlation. All right, and actually this is the long story. That was a kind of a long story with some long development. I should acknowledge many people at this point, but I start from the conformal field theory, from ordinary differential equations. But let me just drop it at this part, because especially at the moment, the most developed part of this theory is related to the quantum dotted systems, and the Singe-Gordon equation is some of the simplest this family of integrable field theory. But my questions here, well, it looks like that the approach, this correspondence between quantum and classical system, is a general approach. And then, of course, the most interesting question how to apply it for nonlinear sigma model, which is probably most interesting quantum integral quantum field theories, which has a lot of applications in condensed matter physics and string theories and so on. Here I want to discuss this, how describe this correspondence for some simplest case, of course. And the simplest case, I'm going to use certain sigma model, a certain deformation sigma model on the three spheres. But again, let me start with the quantum mechanical problem. So, quantum mechanical problem here, it's in principle, it's a textbook from classical mechanics, perfect classical system. It's a system, just a rigid body. So we consider, let me start with a classical rigid body Lagrangian. So the configuration spaces institute the orthogonal matrices which describe the rotation of fixed systems and the moving system. That would be what ignoring this problem with this, we can actually ignore the difference between SO3 and SU2. So in other words, our configuration spaces as a group, SU2, which is spheres, right? The three spheres topologically, and the Lagrangian, the quantum mechanical Lagrangian can be in this form. And another way to think about this problem is in the case when all inertia are the same. And so in this case, the metric, we can think about this problem and the problem of the particle on the three spheres. Right? And the metric on the matrix is just a round metric on the spheres. Alright, and I'm going to use certain coordinate. So the Hopf coordinate probably the most convenient at this point. So we parameterize the group element this way, so it shows explicitly equivalence between the element, group element and the sphere. Then introduce the Hopf angles and I1 and I2, which are periodic, which is so it's quantified variables. Also, I will use zeta. And sometimes it's convenient, since zeta is between -1 and 1, then sometimes it's convenient to replace by the angle beta. All right. Then, in principle, the relations, here the formula which relate the Hopf coordinate and the Aileron angles, and this is the standard Aileron composition for C2 group element. And here is the explicit form of the matrix. You see, this is the Aileron angle, right and left Aileron angles, and this is the angle. Alright, so this is a round sphere. This is a metric of round sphere. But of course, it's not particularly interesting. But it's more interesting to consider the deformations. And the deformations I'm going to use here. It was proposed by Kate in 1996, and the matrix looks like this one. So we still use the same coordinate. Topologically, it's still three spheres. We can use the same coordinate as on the round spheres. And the metric element, so the matrix, non-trivial element of the metric, here explicit formulas, they do not depend on the angles, on the Aileron angles or Hopf coordinates, so this still killing coordinates, so the metric is possess the isometries U1 plus U1. And the metric depends on three parameters here, kappa A1 and A2, and as kappa equal to 0, then we return, if you substitute kappa 0 in this formula, so then you return to the flat, to this round metric. But indeed, when kappa in between 0 and 1, there is a certain deformations of the round sphere metric, so the symmetry of original O4 symmetry is broken down to U1 plus U1. All right, and now so we have this system. Now we consider the particles which move in on these different spheres. And since we have two U1 charges, we can write the wave function in the separated separate the variables, write the answers in this way. Q1 and Q2 are conserved charges. We can do conserve charges. And for material dependent side, zeta dependence, actually, if you substitute these answers to the Schrödinger equations, then you get the equation famous Cohen equations. It's equations with four regular singular points, right? The singular points located at the point 1 kappa, 1 minus 1 kappa minus kappa minus 1 minus 1 of the kappa position of the singularities. The parameters delta I related to delta I is a coefficient in at the second order poles. They're related to the charges of this. And also there's additional four parameters, CI, so-called accessory parameters, but they're not independent. The condition that the equations doesn't have singularities it's actually regular, and at infinity it leads to three additional relations, and in other words, only one accessory parameter actually independent. All right, and so we have this equation. Now we can consider with work as an quantization conditions. I will talk about the neutral set. So the charges, both charges U1 charges to 0, so it's a neutral state. So and the solution is similar to the case of the modified synergy-Gordon equation. The exact Boltzmann quantization condition is known. In this case, it can be written this way. And so this is the total factors, and this is a bunch of gamma functions. And the function f, which depends on x, and x is just a cross-region, right? Or the which is built from the positions of four singularities. This is the implicit formula expressed in terms of the kappa. That's the integer here. All right, and now let me consider, so the semi-classical conformal block admit the regular power series expansion with, well, if you with the logarithm, there's series expansions. And for small x, when kappa goes to 1, x goes to 0, so we can ignore this series. And with the exact Boltzmann quantization conditions turn to the condition like this, right? So this is very similar, almost the same equations as the modified Mackey equation. The effect is slightly different here. But I should emphasize the k equal to 1 is the opposite limit, opposite to the case of the round metric, kappa equals 0. And we will discuss geometry and what happened with the deformed spheres in this case. And let me explain what happened. So this is almost limit to the case of round spheres. So as kappa goes to 1, actually it is useful to use the whole manifold can be covered by two charts. So here are the explicit formulas and reduce the capital. And then in each chart, so the one chart, another chart, and each chart the metric looks like this. Right? And in between you have a cylinder, right? Actually, this is a segment times two torus, because it's three-metric. I just this cartoon is just a two-dimensional image because it's three-dimensional surface actually. But anyway, in the between and as s goes to 0, the metric almost flies everywhere. It's like a cylinder. So in the central region, you see the metric is just flat. You can introduce the coordinate, introduce the field metric. It's a flat metric. So this is a cylinder. So this is a U1. This is a two circles, and they correspond to the segment. All right, and this is described the metric in the region, in central region, as x goes to 1, and the coordinate x r and xl is code. All right, but in the ifs now, if you consider the if, then the matrix on the chart, then the matrix actually the sum of the circle, matrix on the circle, and the Euclidean black hole, Witten cigars. And then this equation can be interpreted in very simple interpretations with just effect of this delta. It's just effect of reflections on the tips of the cigars. So it's so-called classical reflection amplitude within cigars. So the meaning of this amplitude reflection amplitude is quite simple. And of course, this is we are talking about mini superspace. We are talking about the mini superspace distribution. We are talking about the particles on this background. Okay, so now you see that with the particles, the problem with the particles on quantum particle and Partier sausage needs to the Kane equations to the one principle can be expressed in terms of conformal block, but there is some interesting relation between the classical conformal block and the Pindel's equations. We'll discuss now with Alyosha Litvinov, Nikita, and Sasha. So the classical conformal block can be actually identified with the actions of Pindel's six equations, on-shell action coupled in certain solutions of Pindel's six equations. In this way, we have I not have time to describe explicitly all the relations, but what's important for us that there is a certain correspondence between quantum particle and Partier sausage and Pindel's six. And this correspondence is very similar to that we discussed for the particle in material cost potential and Pindel's three equations. Okay, so this is now of course the question how to generalize this for the quantum field theory, and for example, it's quite clear that we can consider now the 1 plus 1 dimensions, right? Now x and start with the action in this form, which is just a straightforward generalization of the case of the rigid of the symmetric rotator when the theta parameter was allowed. So this is an action. So this model is a famous model in calculable two-dimensional quantum field theory, principal chiral field of O4 model. And a lot of factors known. It's a classical integrable and normalizable, and also the factorizable in the quantum. It's quantum integrable. Integrability is preserved from the quantum level, so the S matrix can be actually. It's not difficult to guess the S matrix using the Jan-Buster cross-infinity and unitarity relations, and also global symmetry. So this expected form of the S matrix, which is a tensor product of two SU2 invariant solutions of Jan-Buster equations. And I use this symbol infinity. You will see the need to why what I will be explaining in the next conference. So basically, it's just a permutation, right? Up to the overall factors. Okay, and the model need deformations. Just reviewed it. First of all, we can consider deformation. The global symmetry was SU2 and SU2, but you can deform it by adding the additional terms here, which is explicitly brought the right invariance down to U, because this is clear. Now, so we introduce additional coupling. And but the system is classical system, and the classical level is classically integrable, it's renormalizable, and particularly the combination R and U, we have two couplings now, and this combination of the couplings, it's a G invariant. So it doesn't hold, so it's parameters of the theory. As for the factorizable spectrum theory, then the S matrix is the deformations of the tensor product described before. And one of the area, the symmetry now is U to U. So the SU2 component remains the same, but right part replaced its deformations of SU2 invariant solution to U1 invariant solution, which is a coincide with a S matrix of Sine-Gordon S matrix, and the parameter A here is what's so-called normalized coupling for the Sine-Gordon. As A goes to infinity, you see R goes to 0, A goes to infinity, and we restore the SU2 symmetry. So this is the formula. And finally, in 96, the Fatih proposed the deformations of this form. This was from his paper, based in this form. Introduced now it approved right and left current. You see now the four couplings here, U are three couplings, U, R, and L. And now you can, and this is of course a sigma model exactly on the metric I described before. Just a different coordinate, and a different coordinate, but the parameters, remember that in the metric we discussed before, it was a parameter A1, A2, A in kappa, and then here is the relations between these couplings. Actually, he found this metric by solutions of realization group equations, Ricci flow equations, and this found these two parametric deformations. In particular, under the realization group flow, the parameter A1, A2 remains the constants, the G invariant, and kappa flows. And in ultraviolet beam, kappa goes to 1, that corresponds to the deformed matrix, which looks like a sausage, right? For this reason, it's called Fatih sausage, the dimensional sausage. And this is ultraviolet limit. Sorry. Ultraviolet limit, and as kappa goes to 0, as kappa goes to 0, it's around spheres. And this matrix was proposed, also Fatih proposed this matrix. The two parameters A1 and A2 are realization group invariant for this metric. Interesting that classical integrability was established quite recently, 3 years ago, at my work, and later in Vinci found this another representations, another zero representation for the same model, and actually this representation equivalent. Okay, and now the questions, what would be the energies, how to describe the energies, and these are the systems, finite computed system in finite volume. That is, gives us, in thermodynamic Becker-Nassau equation we proposed in original Fatih form. Actually, it can be applied only for the case, the couplings, A1, A2 integers, for the integer couplings described by the TBA, depicted on this, or labeled, encoded by these Dingin type diagrams. Later it was found nonlinear equations, which works for any values of couplings. But the question is that it's not whole story at all, because now about the Hilbert space of the theory, clearly we have two U1 charges, and the whole sector, whole Hilbert space of the theory is split from the sectors labeled by the conserved charges. But Q1 and Q2, which should be integer, of course. But we can also consider the boundary condition, consider the so-called winding boundary conditions, and in this way, and which is consistent with the U1 cross U1 symmetries, and so the boundary conditions labeled by two quantum numbers P1 and P2, which is actually should be defined modulo to integers, right? And then the whole on the circumference, and also depend on the winding numbers. And the PDA equation, which was described on both PDA and LE, it works only for case K1 equals K2 equals 0. And So the problem is quite difficult because it's not clear how to do. At least I don't know how to do using this method, how to calculate the spectrum in the one sectors. So, but nevertheless, we can find the estimated behavior of the energies in the short distance limit, again using the kind of modifications for mini superspace approximation, replacing by the mini superspace amplitude by exact black hole reflection amplitude. So this is basically including the functions. You can use the approximations of the energy, which works pretty well for sufficiently small r. As for the large r limits, in this case, for large r, the system developed the extensive plot proportional to the volume, to the size of the system, so that with a certain part of energy, which is known here to forgive. And then the correction can estimate kind of corrections, like similar to Lucian calculations. And they come from that virtual trajectory which wind the circle, and each solitons well, add additional factor depending on winding, and combine the simple calculation leads to the following leading correction, exponential correction to the winding energies. So in other words, we know and here is how it can be in this picture. You see this is the solid line represents the ultraviolet asymptotic, the dashed line represents the infrared asymptotic, and the dots is just the solution come from the solutions of this system. So you see it pretty well. Okay, and now I have only 5 minutes, but so what would be the idea how to what kind of classical system can be solved with this problem? And to explain this, I need to introduce the dual descriptions of this Fatih sausage. So it comes from the very simple ideas. We remember that the sausage in ultraviolet limit, the sausage mostly is a flat. So this is a metric. And then we can perform, if you perform the duality transformations for the U1 coordinate, killing coordinate, so this is preset formal, then the conserved currents, so satisfy the conserved equation. If you resolve this equation in terms of dual field K1 and K2, then Lagrange will take this form. So in the central region. But then you use the idea of Alyosha-Zamolodchikov, which proposed the dual description for the black hole. And since in the tips, the theory described by the black holes, the original proposal was the Zamolodchikov proposal. What this can be described in terms of so-called sine-Liouville theories. And in this part, we have also additional U1. So in other words, once you consider this part of the metric, you can, well, dual description will be given by the flat terms, kinetic terms, plus the sine-Liouville which come from this piece. And these things of the cigar describe another cosine. It's very naive just to add them together, but it works. And remarkably, that this naive procedure worked pretty well, and Fatih gives some argument, well, actually calculating, make some real calculation, and show that this Lagrange indeed is a good candidate to the dual descriptions of the sigma model. And here you see the parameter is alpha 1, alpha 2, and D, which is related parameter. So we have a Fatih now, it's some numerology. So Fatih, I will call the Fatih model the theory described by deceptions, right? And described by deceptions, and this is the relation to coupling not independent. So in the regime, which are actually interesting for sigma model regime, alpha 3 decoupling is pure imaginary. So this is a real component, so Lagrangian is real. So of course the theory is unitary theory. But in principle, you consider the theory in the case when all the current can measure, in this case, a kind of symmetry between all the fields P1, P2, P3. So I call it a symmetric regime. In this regime, you have a period, clearly the potential is periodic. This is the symmetry, and all this spectrum, all the space of state can be split on the spectrum which is labeled by the quasi-momentum K1, K2.
There are systematic means to obtain
thank you. All right. Yes, it's square is too much. Too much. All right. So this is a one-year number. In the symmetric regime, we have a one-year number. In the sigma model regime or unitary regime, we have only two number quasi-momentum. So because there is no for real exponent, there is no such. You cannot shift the field. It's not allowed. So, and of course, in the sigma model description, this point, this quasi-momentum should be identified with the one-year number of sigma model. All right, and then now I need to use the result of our work about the symmetric regime. In this work was proposed for the Fatigue model in sigma model in the symmetric regime. So this is equations. So it should consider on the three spheres. It's still kind of modified, so-called modifying Sinch-Gordon equations. It should be considered the three spheres. This strange object transforms like a quadratic differential with respect to P and 2C transformation. You can move the whole singularities in desirable positions. But anyway, so by the Christoffel-Schwarz method, we can map it, the problem to the ordinary, to the standard form of Sinch-Gordon equations. And but in it, after the transformations, the three spheres maps to this polygon with the proper modification. So, and in other words, we have a Sinch-Gordon equation in this strange domain. And if you solve the equation, so my proposal was the solutions. If you solve these equations on this strange domain, then the energy for symmetric regime, non-unitary regime, and given by this formula, similar to Sinch-Gordon actually. And then later with Volodya Bajdanov, we found the system of integral equation, non-linear integral equation, support all the conjectures, and indeed consistent with the factorizable scattering theory associated with the Fatigue model in symmetric regime. There's some quite complicated. You see there's some bunch of particles here, but anyway, they all the consistent with it's all consistency descriptions of symmetric regime. So and now the idea of the work is quite simple. We just take the same with our differential equations. We just trying to analytically contain the differential equations in the Kaplan constant. And there is not much problem with this. You can think about any parameters in the equation in any for any values, right? So the regime, the symmetric regime corresponds to the case when all constant. And the regime which seems which is just a formal analytical continuation, or to the unitary regime corresponds to the case when one of A coupled A3 is negative. In this case, but still, of course, the Christoffel-Schwarz matrix looks quite different. In symmetric regime, the domain looks like this. In sigma model regime, it looks like that. You see the one of the vertices close to infinity. But anyway, the idea is just to continue to work the result of the formula, just use this as it is, and calculate numerically solve the differential equation, partial differential equation in this strange domain, and calculate these quantities, and compare with the asymptotics, short distance asymptotics, and large distance asymptotic, which comes from the very simple argument I presented here. And that gives that looks pretty well. model, it's a Pagiev model, I said, because two S matrix, right? S plus is not correct. Alright, anyway, I didn't discuss non-linear equation, but since we covered classical differential equation, principle, the equation non-linear equation also known in this regime, but numerical solutions looks like not particularly good. The convergence is, I don't know, maybe that's a question about it. And also in principle, all this stuff can be generalized for exact dimensions. And of course, this is quite technical, and I hope it will be finished. But the most interesting is generalized for the sigma models, particular, for example, this SS model is a just a sort of subset family of four-parameter deformations. And in this case, some interesting little infrared points, so it's quite interesting to see how this infrared behavior here. And also, well, the generalization, certain generalization for the higher group, and of course, it would be interesting to generalize all this stuff for the supergroup as well, because it's probably most relevant to the subject of this conference. Okay.
How you plan to see. So you have a Pagiev model. On the one hand, you want to find quantum spectrum and quantum energy. This is one side. Now the second side, you say, take Pagiev model, classical equation of motion to this model, and make a manipulation manipulation until you go to Sinch Gordon. And that's when the Sinch Gordon you recover quantum spectrum.
No, so maybe I don't quite understand your question, but I should emphasize that these relations has nothing to do with the classical limit or the classical.
Of course, I understand. So, but how do you explain that vacuum energy in the sector of the model is given by this whole Sinch Gordon is also
So the vacuum energy, for example, or maybe if you want Q functions, the vacuum energy is an example. For example, you have a quantum system, you have a bunch of quantum transfer matrices, you have Q functions and stuff like that. And all this quantity can be interpreted as a connection coefficient for the classical inverse scattering problem for the classical integrable system. And in this, I just use the energy to explain how it works for Q function, for example. It's more interesting, of course. But the energy is the simplest integral of motion.
Yes, so my question here, it seems like you like some kind of derivation. Don't think you actually. Well, when you derive these classical equations, quite classical equations, started from actually action model.
Well, classical equation for what? Classical, we have quantum systems, we quantize it. We have quantum systems, for quantum systems, for example, we.
Well, until you map to differential equations, right?
But this is a quantum system, and another part is the classical system, classical differential equations.
Yes.
And they actually, the quantities, let's say, the integral of motion, all the quantities decreed in quantum state can need the interpretations of, need the interpretation in the quantum system.
So did you give any hint how to derive this? So you just take it similar to each other.
Yeah, sorry?
Did you give any hint how to derive this?
Well, it's a long story. You see, I left the bunch of, well, actually, basically, it's based on the spectral curve. But the spectral curve is the main guess. If you know the spectral curve principle, you can guess the classical system. But it's not straightforward. I don't, unfortunately, know what is the general procedure. If I know that, you know, just try to demonstrate that maybe works for some example. You know only an example, but not a general procedure.
Okay, well I think lunch is proceeding further and further into the future, so we thank Tony again.
But I don't know but remember, this is the definition of the signal side, not from the outside. That's but I didn't know.
Okay, so last speaker this morning, last speaker today. About form factors.
Yes, so first of all, let me thank the organizers for giving me a chance to talk at this nice conference. And so I am a little bit ashamed to talk about the four factors. So when I would propose, so I don't know, I was not thinking about it for centuries, but so then somehow I decided that probably is not so bad because so there is some, it will be related to some project which we carry on with Sasha Zamolodchikov, and I would not scare you telling for how long the project is carrying on. So, and still not. Anyway, so I will begin with some explanations about, simple explanations about the four factors, and so I want to underline the points which are often explained. So we have, suppose we have relativistic two-dimensional integrable quantum theory. Yes, and I didn't say that I will mostly talk about relativistic models, but so at the end I will say something about lattice models as well. So suppose we consider relativistic integrable model, so the spectrum is like that, yes, and so particles, so actually, for simplicity, let's say that there is one particle, but it may carry isotopic indices, but so actually all this thing is generalized to many particles. So for example, you can put them into one huge multiplet. So then my convention is when I write S of beta 1 minus beta 2, and this is isotopic. It means that this thing belongs to the tensor product of this isotopic spaces related to first and second particles. So with rapidity beta 1 and beta 2. So in this matrix is well known from, for example, from very old paper by Zamolodchikov. Zamolodchikov is basically described by three equations. So first we have scheduling is structurized, so there are cluster equations, then there is unitarity. So actually, so there is some unitarity, so I must also explain that S of minus beta is actually S of beta, S star of beta, that's what is another story, and crossing symmetry. So crossing symmetry, so it involves some matrix, or rather tensor, because it just lowers index. So this is a transplantation with respect to the first isotopic space. If there is isotopic degrees of freedom, and the C acts only also on the first space. So there are three axioms for factorized state. So now suppose we want to compute the matrix element of local operators, and so we start with vacuum, so with the matrix element between vacuum and excited state. So we start with for example, from some asymptotic state, for example, in state with ordered rapidities, yes, in this way. And then we start to do something. And so often people say that from the first principles of quantum field theory, it follows that the result will be analytic and paramorphic function and so on. I would like to see anybody who can prove it from the first principles of quantum field theory, because analytical behavior, even in this simple case, analytical behavior in opposite direction and to formulate some properties of these form factors as axioms, and then as Greeks explain to derive from this axioms a theorem which do not contradict to a common sense. Yes. So first axiom is that this zero axiom, which is actually I would say the most complicated one, is that the result of this so from here, from this I can continue from the domain, I can continue analytically, and the result that it analytical meromorphic function of all the arguments in the entire complex place with some poles. And so some of these poles are also fixed. So then there is the symmetry. So if I intertwine two particles by S matrix, and once again I have to say that in principle I have to write. So this is the covector for me. Yes. So that's why I from my operators from the right. So in principle I have to write commutation here, but I understand that if two particles switch the place of the isotopic space, is also switch the place. So another axiom is that if I shift by I, so and if you wish, so together with this thing, so I can move this particle back, and I will have some equations that I have a function with this beta n will be shifted, and then it means multiplying it by some huge product of S matrices. So this is a Riemann-Hilbert problem on a strip. Yes, so I have for this function, so analytical function on a strip. So on two lengths of the strip, I have some connection matrix, which is a product of this S matrices, which I needed to in order to bring this thing back. So another name for this equation is quantum epistemological equation. Yes. Special case. Right. So then comes one more thing, is that so all that was mentioned already yesterday. There comes one more thing, that there are poles when two rapidities are annihilate. So when two rapidities are shifted by pi I, so for identical particles. So so from n particle form factor, I get n minus 2 particle form factor. So this guy lives in the tangent product of n spaces. So this guy lives in the tangent product of n minus 2 spaces. I have to compensate. I multiply by some vector, so which is exactly the crossing symmetry delta which I had before, and 1 minus. This was the most complicated thing to guess. And so then if there are bound states, so they make a bound states. So then there will be poles also when these two particles, say number n and number n minus 1, can create a bound state. So then there are poles on the physical so like that. And so the residues are related, of course, to the form factors of these bound states, but this is kind of more or less obvious. So gamma here is the vertex, so square root of the residues of S matrix.
Does gamma depend on some beta?
Gamma, no, this is just
The number.
Huh?
The number.
Sorry?
Does it depend on beta?
S depends on beta, but so this gamma is square root of residues of this S. S depends on beta. Yes, so square root of residues of this S at this point. So residues does not depend on beta, right? So and now. Another thing, which is usually said to be trivial. Yeah, yes. So now with axioms, I will prove a theorem. Yes, so a theorem.
So, and what I want to do is to describe the, so having this form factor, to say how I construct the matrix elements between two different states. So a simple thing is the basically it of course must be done just by a crossing symmetry. So I can bring some number of rapidities from this right from this ket vector to bra vector, yes, just by shifting by minus pi I. So this is okay, transformative transposition and applying this crossing symmetry matters, but just because of crossing symmetry. But the question is, how do I understand the singularity? Because so there are effectively they are here separated by pi I, and there are singularities. And the people usually say that so these are some disconnected paths which you have to ignore. So but it's not so trivial to guess a formula. How do you really to write a formula? How do you really understand the singularities? So here I start to use some notation which I think clear. So these are sets of rapidities, this A and B, ordered sets of rapidities. So I consider element between two states, yes, and so delta here is for two sets is a product of delta functions, and if there are isotopic degrees of freedom, also Kronecker symbol with respect to isotopic indices. So the way of, so if you wish, this is another axiom that the matrix element of between two excited states is expressed in terms of this form factors, so in terms of this f defined here in this way. So they were this is plus I0, but okay, this is how the singularities are understood, and I did this S are, so we have factorized this matrices. So suppose we have some set of rapidity, and we have a subset V1. So and we want to put it to the left. Yes. So then some product of S matrix like this with M. See. So and now I will prove my theory. But so another thing that so before, if you want to prove a theorem, you first have to prove lemma. Yes. So lemma says that I can change understanding of singularities here. There's an equivalent formula which looks like that. So they are rather similar, but you see, so there are some minor differences. So the important difference, of course, is here. I understand that as plus I0 here as minus I0. So in a sense, it's about in and out states. But so how do I prove it? Just you see, so changing plus I0 to minus I0. So I get poles for here, and the residence I know they are given my annihilation poles axiom, and so that's why I just resum something, and I arrive at. So there are two equivalent formula for the matrix element between two arbitrary states. Now, what do I want to prove? What's the theory? The theory is that with this, from this axioms, locality follows. So, and so yesterday I was listening to these talks about the form factors from Pedro and from Yannick. So I thought that all that is nice, so you can introduce axiom, but you have to prove something. So, for example, so I don't know what you have to prove in this string case, but you have to prove something. So here I prove you have to, so from axioms you have to derive theorem which goes along the common sense. Yes. So from my axioms I derive the operators whose form factors satisfy the axiom, they commute on a space like this.
Let me just make one comment.
Yes.
We did study your theorem very carefully, actually. I found it very beautiful. And indeed, the analog for us would be to show, one possibility of an analog for us would be to show that our axiom would imply crossing symmetry
Yes,
for
what I mean.
functions,
Yes.
and for correlation functions that it would imply channel duality in the same sense. So, but it's a bit more complicated because
Yeah,
it's
so
relativistic invariant and having a little bit more, but it's definitely.
Cross is what I thought about yesterday. Yeah. So, okay, so they compute on a space-like interval. So, since everything is relativity invariant, just let's take space interval. And so let's consider these two guys. And so the trick here is that I take for one of them, I will take one of my representations for the matrix element, and for another given by lemma. And then, so for this matrix element, so I will have kind of I put between the complete set of states, and for this matrix element, I will have some rather messy thing. So because this A and B now will be divided into several subsets. So some of them will go through directly. So you see this is this A3. A7, I have this sum with respect to intermediate state of integral with respect to rapidities, and when I put vector here with the rapidities order or rapidities of this intermediate states, and so then of some function, which can be computed. And I'm sorry, the result is a little bit long, but so it looks like that. So again, there's a bunch of multipliers which I don't care at all. But here, this is from one part of the commutator, and this is from another part of the commutator. And now the miracle happens because you see this thing, for example, this one, allows analytical continuation when I move all the rapidities from this set C to minus pi I. Because so you see, so here minus pi I is okay. So here minus pi I is also okay. And here minus pi I is okay because so this exponent, if x is less than y, so this exponent will be from in the street from 0 to minus pi I will be small. So, and what will happen when I shift by minus pi I? So, first of all, this guy, the first guy, this will shift here. So, which means that it will come, according to my definition, it will come to the left, yes? So, so this will be like that. So now, what about this one? This one will shift minus to minus, it had minus pi I. So it has now minus 2 pi I. So it will come by my Riemann Hilbert to the right, yes? So, and you see that this, so now you have to make translation something like that, but basically, so these two terms will cancel. So, that's how the locality works. And it is obvious that in principle, so that this thing, this K of C is of course, so I didn't say sorry. This is the total space momentum, yes, for this. And so this K of C in my strip, this expression in my strip decreases so fast that the form factors in principle can grow as a power of beta of e to beta at infinity. So now this is that. So if you have questions about this, you can ask. Now I go to problems. So there are several problems related to this. So first problem is to have examples. So that this axioms were completely solved for many models. So this problem is all right. Now to identify, you see. So also it has been said yesterday, but the important thing about the four-factor axioms is that they define all the operators. So these equations, the four factors of any local operator must satisfy this axiom, yes? Or, according to my logic, how to say, if four factor of some operator satisfy this axiom, it is local, yes? Yes. And so, but the question is, on the other hand, so suppose we have something like, so suppose we have some ultraviolet description of the model. So suppose this model is, for example, is a relevant perturbation of some conformal field theory. Then basically the space of operators must be the same as the corresponding conformal field theory. So how to check? And so this problem of identifying the solutions with conformal field theory on a qualitative level for Stein-Gordon model, for example, it was done. So then for quantitative level, it was done rather recently by my work with Jim Gordon-Miller, so using thermodynamic waves, stuff like that. So, and what makes me very nervous, and so actually I'm working with this now, like, so that I cannot give, I can write some operators, but definitely the solutions for fact equations which I can write all the operators. This is actually something very complicated. So this is another thing. So problem is as follows. So you see, so we consider this commutators. Yes. So suppose we. So mathematically speaking, so what exactly this statement means? That the commutators are vanished on the space-like interval. It means that they are distributions with support at zero. Yes. So now, from time to time, it's interesting to know what are the delta, the derivatives of delta functions at zero. Yes. So, and this can be understood because if I in the sense in the proof of my local commutativity theory, I take a convolution of this commutator with the function which decreased at zero with all, and of course infinity as well, with all the derivatives. But I can is this requirement requiring that it vanishes with I don't know, with 1, 2, or 5 derivatives, and see what will happen. What will happen is that if the form factors of this operator grow at infinity, so then this thing will behave at infinity, and Fourier transform will behave in infinity in a special way, and form factor also grows in a special way. And then I can somehow derive what will happen. So I can see. So when I deform my contours, I will pick up as usual some contributions from these intervals from my work. The ends, yes, and compute these contributions with delta prime functions, and so all this works in many cases quite nicely. For example, so you can derive the current algebra for sigma models. So, but the last thing, which is the last thing which I did not mention and did not discuss yet is the conversions, because so you see from in some sense, so when we are talking about these models as Stein-Gordon or some known models, so we believe that the green functions and that everything is not defined. Yes, so we don't really care about the conversions. But so in general, this is from mathematical point of view and from practical point of view, as we will see, this is a problem, because so I have shown that the commutators vanish term by term. But the question is, when I started from the original matrix element, so the series with respect to n, with respect to number of intermediate particles, intermediate states, the series will converge or not? And this is a hard question. And so from time to time, it's possible to but not necessarily conditional, that the number of particles here is n, so then this for is estimated as something which depends on this guy, which is not very important, but as some constant to the power n. In that case, these series are estimated like that, and you see that they are convergent. E is one particle conjugate cosine, and you see that they are convergent, and even for their singularity at 0 is not worse than the power like. But this is possible to do only in some cases, and so this is not so easy. Okay. So now I hope you know now everything about four factors, and I go to an example. Examples are favorite examples. I go to model. So now I write only one dignify here. Yes. And so this is the action. So this is the S matrix. So okay. So the solid tones, that is solid tones, they scatter. So this is they belong to one multiplet solid tone and uncertain tone. So they scatter. So this is the S matrix 4x4 S matrix for the scattering, which is found by the Molotchikov many years ago. Psi is the Halpern constant, and normalized Halpern constant, like here. So yes, all that I don't. So now the model of integral, what does it mean? It means that there is an infinite set of conserved quantities. So namely, there are conserved currents. So S is arbitrarily odd number. S will be always odd here. So there are conserved currents which satisfy this conservation equation. Yes, so there are kind of when S is equal to 1. So this is will be just the energy momentum. One component of the energy momentum tensor is the base of the energy momentum tensor, and so in general, so this is like that. There are infinitely many local conserved quantities, and therefore factors all the same basically, because all of them are obtained from one set of functions which I call G, and so multiply by something like that, just depending on which one you want to compute. And this G are functions which satisfy more or less the same axioms as always, but so there is one small thing that if two particle four factor has this multiplied higher pole. Two particle four factor has double pole and beta 2 equal to beta 1 squared. And then when I multiply by these two things, I see exactly kills this double pole and I obtain local operators.
Excuse me, is it a non-zet or is it that you can prove that it must take this form?
It is, so it's kind of, you see, so it's here, so what does mean? D minus means multiplication by sum of b to beta, yes? So D plus is multiplication by sum of D plus. So that's already, so a part of this guys is clear. So and then so what additional thing is that this from this two particle four factor, yes. So you derive the eigenvalues actually of this integral of motion on n particle states. And so if you a little bit play with this, you'll see that this is the only possibility. This is not an ansatz. Of course, so in a sense, so you can add whatever you want. You can add the total G.
No, but this G is a form factor of a non-local operator. Can you write a non-local operator explicitly?
No, I don't write non-local operator explicitly. So it's a logarithm of tau function. Yes, classically, right? I don't know what is correct. So I just wanted to say that all these four factors, something this guy, these four factors are all the same, but something strange happens only for one case, only for two classical four factors. And we have something similar later in more interesting situation. So we can discuss it later. Okay. So now one more thing which I want to mention is quantum group reduction. So there is our old water initiative. So actually, you see, so this S matrix is invariant under the action of quantum of affine quantum group. Q is equal to half, and Q is like this. So if you don't know what this the affine quantum group, don't worry. Anyway, so invariant under something. And this affine quantum group contains two finite dimensional quantum group, and let's take one of them. So for one of this guy. And so looking at this four factors, so for example, or by some other means, so you make sure that this kind of operators, for example, yes, with M positive only here, they are invariant under one of these quantum groups. And that's why, so if I compute, for example, the correlation function with many of them, so I start with zero, with spin 0, and I want to finish with spin 0, and then I have some intermediate, so how it's called, some in the matrix elements, I have some intermediate, yes, so, and I can parameterize them by this staircases of intermediate spins, yes, so they jump. They start from 0, go to 0 because the operators are invariant. And then jump by 1/2, so every particle is of spin 1/2. They jump by 1/2 up or down, and so all of them are positive. This is the requirement. But then interesting thing happens when Q is a root of unity. Then automatically for these operators, all the states which do not satisfy this condition, if Q to R is equal to Q to R is equal to 1, all the states which don't satisfy this condition will disappear from the correlation function. So just for simple kinematic reasons, so some scalar products will be 0. And so this is how the restriction of Stein-Gordon model happens. So I want to emphasize the point which is also often not quite well explained, so that this restriction is a non-violent procedure. So if you just take proper operators, so all the wrong degrees of freedom will disappear themselves. And there are most interesting examples of this are, first of all, if beta squared are like that, so Q to the first equal to 1, then, so the simplest example is this Yang-Lee model. So then just solid cos completely disappear from the spectrum because there is no place for them. And so there will be only bound states. Solid cos will completely disappear. And another case is when beta is 3, beta squared is 3 divided by something. So the simplest case is 3 over 4. Then the only allowed spins will be 0 and 1/2. So a little jump from 0 to 1/2 like that, yes? And so, which means that essentially, so the soliton will be reduced to scalar particles. And the simple case with 3 over 4, this is just Ising model. So Ising model is. So now the question which we studied with long ago is the following. So now suppose I make a perturbation of my Stein-Gordon or any integrable model. So then in the first order of perturbation theory, so the S matrix will get the following correction, yes? Just correction will be just, so if I perturb by operator O, I have to integrate this guy. So I have to put the form factor and integrate the form factor over X. This will be give you delta function, and then the form factor. And then obviously, in general case, the factorizability of scattering will be broken, because and for example, to process, because this non-factorized corrections will appear, right? So this I found operator will satisfy following requirements. So first of all, its two-particle form factor is equal to 0. That's okay. So then, if its two-particle form factor equal to no poles between this, for example, in general there won't be poles here, but here there are no poles. So this four-particle form factor is well defined. And now suppose that all the form factors for higher, say 6, 8 particles, and I don't know what else, so they will have this form. So this is, if you wish, the P plus, total P plus, and this is total P minus, yes? So then what will happen? So all these guys will vanish on delta functions, right? Because this is delta function here. So that's why there will be no non-factorized contribution to the perturbation of S matrix, and there will be only contribution to correction of 2 to 2 S matrix. So which means that just our factorized S matrix will start to modify a little bit. So how it so what is the examples of such a case? Actually, there is, because so if we remember, I have this conserved quantities, this TS and TS bar. So if I have this composite operators, so just product, I don't explain how I define it. So there are several. So there is a kind of way which Sasha explained, and there are also, and we can do it with our theory basis with the Jim and Leo. So anyway, so I can define such a composite operator, and they exactly satisfy these conditions, right? Which means that, and moreover, I can compute this important function, and it is given by this constant here, which I write just for fun. But essentially, it is just product of two sides, and of course, it's just singles. So then, of course, so this is now we are in a very delicate position, because these operators are all irrelevant, right? And so what does it mean to perturb by these operators? So from the point of view of canonical field theory, so I want to write something like that now, yes? But canonical field theory, what I am writing here is a horrible mess, because so these guys contain high derivatives. Yes, high. Yeah. But let's be brave and try to write something like that, yes? So then according to this computation which I showed before, so the result of in the first order of perturbation theory, higher order of perturbation theory, I don't know at all what to do. So, but in the first order of the perturbation theory, the S matrix, this hypothesis matrix, will be just multiplied by such an expression. Actually, I have product of two signs here, there. But so then I recalculate, so there's some Jacobian somewhere, I recalculate delta functions on from P and so one of them tests. So everything is surprisingly nice here. So and this is the only nice to my mind part. And so the S matrix gets multiplied by this thing in the first order of perturbation theory is just a CDT multiplier in principle. I can multiply S matrix by anything which satisfy this condition and this condition. And in the first order, so this condition is all right. S is R odd, yes, as I said. This condition is all alright, this condition in the first order is also alright. But as I said, so since we don't know, actually, we don't understand the ultraviolet description at all of this model. So let's suppose that these are irrelevant perturbations. Yes, so that's why the Kauffman constant, no linear static Kauffman constants are important. Yes. So suppose that these perturbations give us indeed give us sine Gordon model with CDT multipliers. So here is CDT multiplier. So this is one CDT multiplier. I can make many of them, or even if I work very much, I can make infinite minus them. So then this was and this was the first hope that probably for such a matrix it's impossible to satisfy the four-factor equation, and then the problem is closed. So, but it is not so easy. So actually, you can. So let me explain what is the trouble here. So because these two guys, if I multiply by this CDT to satisfy these two guys is easy. Yes, so just you factorize this is scalar multiply, you factorize somehow. This is easy. But so this one is of course here the four factors of the model with the CDT will be very different from the four factors of the model without CDT, because this CDTs will come here, right? So in this problem. But actually, some experience in working with sine Gordon, as matrix, and I know all the solutions to this equation, and I was able to combine them in such a way that this equation with CDT multiplier is satisfied. I can compare many solutions of four factors equation for sine Gordon matrix with any CDT multiplier. Yes, and then the question remains, so law is ultraviolet, because this we don't understand at all. So we start from somewhere even if the theory will be convergence, which I asked, it's quite possible this model. So on some distances, of course on long distances, so everything is exponentially decaying. So it's hard to believe that that's not. But it's quite possible that it developed some finite radius of convergence. So this we don't know, and so this is what we really would like to understand. Why I believe that everything must be more or less alright? Because so consider this restricted sine Gordon case, and consider this beta equals to 3 over 4. So the S matrix will be -1 for Eisenberg method, multiplied by this CDT. CDT is minus CH Gordon method. The S matrix is just CH Gordon equation. CH Gordon exists, right? And so, the procedure, the reduction procedure, which I explained, is non-violent. That's why it is continuous. So everyone believes that function, continuous function, at some point is all right, and everywhere else is bad. This is of course I cannot. So that's why I believe that this series with CDT multipliers, or in other words, this perturbations of sine Gordon, irrelevant perturbations of sine Gordon and other models, of course, exist. But so, what about the ultraviolet description, so and so on? So, this is a huge open area.
Questions?
What about the CPA being conclusive?
Sorry?
What about the CPA that's non-conclusive? For example, we study about branch points appearing when you make
Depends, because if you just, it seems that so if you just take such an matrix and plug it into the GPA, it seems that it develops a singularity as finite radius from here. So then there is what does it mean? So it's not quite clear. And how it relates.
Yeah, I don't need this. Can you, in the higher rank case, can you characterize the operators for which you can compute?
Sorry?
In the higher rank case,
yeah.
Can you characterize the operators for which you can compute versus the operators for which you cannot?
For higher rank, I said that for higher rank, I cannot construct from factors of all almost nothing. The character of W algebra is so huge that so.
Not the operators given by Litvino-Petir conditions.
Why?
There are operators in yesterday's talk by Pomoni, which are characterized by certain conditions, and they're like Virasoro-like.
Like Virasoro?
Yeah. They look SU2-like.
Ah, yeah. So this connected, yes. Like that, yes.
I see.
I have a question about the communication relation of two space-like separate operators. Is it true if spatial volume is finite compact and sample?
No, this is of course true, but so I'm talking about methodology. So in a clear space, that you go one operator along another, and so it's you can get no way. So this is what so. This is so it is a local property. It has nothing to do with infrared environment. Yes.
Well, because form factor with precision finite satisfactions. Form factor with
Form factor with some finite size correction. So of course, this is another story how we prove. I don't know.
Can you deform a local series and get non-local, say, lattice series?
Can I deform the lattice series? So, first of all, start from no, of course. So you see, so this is another application of irrelevant perturbation, and this you can read in the paper of for example, so it's nice to stay there. So you just take irrelevant perturbation, which so you go with irrelevant perturbation go backwards in the notation group flow. Yes, so you can take irrelevant perturbation which breaks, and this breaks Lorentz events, and get from infrared conformal to see like small. But again, so the perturbation is so you can so it is infinitely many terms with non-universal constants.
Is there a relationship with the staircase? You have something relevant to that
Is there any relation? No, there is a relation with the staircase model in the sense that the estimate the CDD staircase. So for example, from Eiden, by the same thing that I explained, I do the staircase. So about irrelevant perturbations, you see here I create many calculations, infinitely many calculations.
questions. So let's thank all the supporting speakers.
now there will be some small